everybody, Mr. G here today to talk about probably the most important force outside of gravitational force, and it's this idea of force of friction. And you may not realize it, but it is pretty much responsible for everything you ever do in a day, from walking to brushing your teeth to pretty much any sort of motion whatsoever. If there was no friction, things would be exponentially more difficult. So we have a picture on the front here of this race car that's burning out, and the real question is, why is it burning out? And hopefully by the end of this lesson you'll be able to explain why that is. So let's start off with some basic definitions. Now the first thing you need to realize is that friction is created whenever two surfaces try to move past one another. You can think of this idea of trying to push a box. When you do that, there's that initial force that you feel that you're trying to overcome something, and then finally it starts to move, right? Well, on the microscopic level, irregularities in each surface impedes the motion. Therefore, smoother surfaces have less friction. Think about trying to push something on gravel versus on ice, or on pavement versus on hardwood. If we zoom in here on SpongeBob driving his hamburger mobile on the road, you'll notice that there are some irregularities between the rubber and the road, and you see all these little jits and valleys and whatnot. Well, those are just the roughness of the actual surface that causes this friction to be created. So the whole idea behind getting rid of friction is this idea of trying to smooth things out as much as possible. If you use an example of bobsledding, they actually work on the runners of the bobsled so much that they try to make it just as smooth as possible so that the friction between the ice and the metal itself is almost negligible. So prime example right there. Now there is an equation that we can actually use to calculate the force of friction, and it's this equation right here. Now before I talk about this, I want to make sure that everybody's clear that in previous topics we've actually been able to calculate the force of friction without needing an equation at all. We've used our net force, and we were able to find the force that was impeding motion. Those questions don't go away, but now if there's additional information about the scenario, there are situations where you're going to be able to actually calculate the force of friction. So this is the equation right here. The force of friction is equal to mu Fn. Now mu down here is actually the coefficient of friction. Now it does depend on both surfaces, but typically speaking it's going to talk about the coefficient of a singular surface. It's going to say the coefficient of friction of rubber is blah, when really it means the relationship between the two surfaces themselves, but we're just going to speak about it in terms of the coefficient for one surface, and that is all. Now the normal force is something that we've talked about. That's the force that results in the force of gravity of the object itself. So it's the equal but opposite force so that it doesn't fall through the floor. Now it's always perpendicular to the surface, which means if we have a sloped surface, you're going to have to consider the angle of that slope in order to find what the actual normal force is, because not all of gravity will actually be creating the normal force. So that gets into trig, which we dealt with two-dimensional kinematics. So always take a look to make sure that when we're talking about surfaces, it's either horizontal or it is vertical or it is some slope, in which case you're going to have to deal with trig. Now there are two types of friction that we're going to talk about in Physics 11 here. First one is static friction. Static's the key word there. It means that the object isn't moving, and it is the friction force that must be overcome in order for the object to initially move. So compare that to this idea of kinetic friction. Once we overcome static friction and we're in motion, now we're dealing with the force of friction that occurs on an object when it is in motion. So there are two different frictions we're going to deal with here. In university you deal with one more, which we won't need to talk about. But generally speaking, the force of friction caused by static friction is always going to be more than the force of friction caused by the kinetic friction. Now we're talking a significant amount. I've seen as much as 10 times as much relating static friction to kinetic friction. So it should be significantly more. And I'm sure labs and calculations will go on to prove that. So let's use these in some examples. A 3.75 kilogram block is pushed along a tabletop with a force of 45 newtons. The coefficient of friction is 0.65. So as soon as you hear the coefficient of friction is whatever, chances are you're using our new equation for friction. So find the force of friction. Well, let's do that. But before we do that, there is something that I'm going to want you to make every single question from here on in, especially with friction and tensions and whatnot, It's the free body diagram. So we have our block. Let's find out what we've got. We've got a force of gravity always. We have the equal but opposite force normal. We are told it's pushed along with a force of 45. That's our applied force. So we'll call that force applicable. And we're going to have the force of friction pushing back. Remember, the length of arrows matters. I'm not going to do the ditto marks to show that they're equal. But at the same time, it's important to know that the applied force is going to win over because it is actually in motion. So, force of friction, well, that's just force of friction equals mu Fn. Now, what is the normal force? Well, looking back to our free body diagram, it's just going to be equal to the force of gravity. So we can rewrite this as mu Fg, which is also equal to mu mg. Now we can actually plug in our values. So we know that the coefficient of friction is 0.65. We know the mass is 3.75 kilograms, and we know that g is equal to 9.8 meters per second squared. Only time g would change is if they tell you outright that you're on a different planet or something like that. So typically speaking, 9.8 is going to be the number you're going to use. And when we calculate this, round it off, we end up with 24 newtons. So the force of friction is 24 newtons. Okay? Now part B says, find the acceleration. Okay, well, now we get into this whole net force idea, Newton's second law, which again is why a good free body diagram will always help you out, because we can see here that the winner is definitely the applied force. It was 45 newtons applied, but it was only 24 newtons of friction. So the force net is going to equal the force applied minus the force of friction. And remember, something important that lots of people forget is F net is also equal to ma. It's Newton's second law. So this whole thing is equal to ma. Okay, so we have this. Let's plug in our values once we solve for a. So we have a, which means a is equal to F applied minus the force of friction divided by the mass. Now we can actually plug in the value, and what do we get? Well, we have 45 minus 24 divided by 3.75, and we should end up with something around 5.6 meters per second squared. So, a typical type of friction question, you would have to find the force of friction in order to find the acceleration. On something like an exam, you might just see it ask for the acceleration, where the part A is just going to be an assumed step that you're going to have to make. So be clear about how we came about these numbers, and you'll be fine. Let's take a look at another example now. Example 2 says a 0.2 kilogram puck is pushed along a sheet of ice with a force of 0.24 newtons. If it moves at a constant velocity, find the coefficient of friction. Now, when we did free body diagrams in Newton's second law, constant velocity was pretty important. Why was that? That meant that the net force had to equal 0. So, let's draw our free body diagram. Here is our pretty puck. We know that the force of gravity and the normal force are equal and opposite. I'm going to put ditto marks on it this time. And then we have the applied force, and we have the force of friction. And in this case, those two have to be equal. Why? Because constant velocity tells us that the net force has to equal 0. Okay, so if we have that now, well, what do we need to do? Well, if we know that the applied force is 0.24 meters, that has to equal the force of friction, equal but opposite, which means the force of friction is 0.240 newtons as well. Well, that's awesome, but how is that going to help us? Well, we have the force of friction. If we take a look at our equation, FF is equal to mu Fn. We're looking for mu. We have this, which means we need the normal force. And how do we find the normal force? Well, again, Fn is equal to Fg. So now we just have to find out what mass times the acceleration due to gravity is. So if we take our force of friction equation and we solve it for mu, mu is equal to the force of friction divided by the normal force, which is equal to 0.24 newtons divided by 0.2 times 9.8, which should give us a value of 0.122. Now, notice that there's no units here, and that should make sense. If we take a look at our original equation, the force normal is in units of newtons. The force of friction is in units of newtons, which means the coefficient of friction doesn't add any units to the equation, which means it's a unitless value. So that's exactly what we ended up with, and that's what we should. So, a little trickier. Constant velocity means free body diagram, super important. Let's take a look at one more question, then I'll set you free. A 1.1 kilogram textbook is held against a vertical wall with a force of 45 newtons. What is the coefficient of friction between the book and the wall? So, we're looking for the coefficient of friction. As soon as you hear that, you should think this. Now the problem is, vertical wall, oh my, oh my. Let's find out what's going on. If I'm going to draw a vertical wall with a book on it. Now what is it saying? Held against a vertical wall. It's not mentioning anything about sliding up or down or falling off the wall or anything like that. Which means what? Well, it means that our force applied of 45 newtons has to be equal and opposite to the idea that this force pushing back is going to be the same. They're going to be equal. Well, what are we going to call that? Well, if you turn your page sideways, you'll notice that it just looks like a horizontal surface, but vertical. There's your normal force. Now, what about up and down? Well, pointing down is going to be the weight of the book, so that's our force of gravity. And now pushing up, well, what's that going to be? Well, it's not going to be the normal force now. We've already accounted for that. The only thing that could be holding it up now is the actual interaction with the wall itself, which means it's the force of friction. So this is a trickier free body diagram. And like I said in the free body diagram lesson, we didn't cover every example. And here's a clear example that goes against the norm. So you have to understand what the question's asking. If not, ask. If not, look it up. Whatever you have to do, try and figure out the scenario before you start calculating, or else you're just going to get it blatantly wrong. So let's start trying to find some information here. Well, we know that the force applied has to be equal to the force normal, which is equal to 45 newtons. Nice, we're good to go. We also know, because it's not accelerating up or down, the force of gravity has to be equal to the force of friction, which is therefore going to be equal to mass times the acceleration due to gravity, which if you calculate it, we put in the 1.1, put in the 9.8, and you're going to end up with a force of friction of 10.78 newtons. Now that we have all those values, let's go ahead and go back to our original equation right over here. And we're going to solve for mu. Mu is equal to the force of friction divided by the normal force. Let's just plug and chug at this point. Force of friction is 10.78 newtons. The normal force is 45 newtons, giving us a mu value of 0.24. And there you have it. So, really important was the free body diagram, because that's going to allow you to conceptualize what is equal to what and be able to solve this question a lot easier. Otherwise, chances are you're just going to start plugging numbers into equations and hoping. And trust me, we all know what you're doing when you do that. So, we've gone through 3 different examples. You'll notice in every example, free body diagram, make sure you have it. Watch your units. Make sure that your mu value is unitless. Otherwise, it's easy peasy. Good luck, and we'll talk to you soon.